MCs. Shreya, are we ready to go?
Yes.
Great. Let's start it off.
Yeah.
Welcome back, everyone. Brush away the Monday blues. I hope you are all even more pumped up after that session, incredible session by Dr. Harish. I take immense pleasure to welcome you all to check this first ever International Research Consortium, an extravagant event with illuminating panel discussions, enlightening and knowledgeable speeches from various respected speakers from across the world, and of course, an ocean of opportunities for you in the form of networking sessions, ideathon competition, and the Research Expo.
Checked In, a student-based research initiative created with a vision that many believe cannot be a possibility. We strive to deal with real-world problems and find solutions that have never been improvised using the help of technology, human expertise, and a touch of empathy. Checked It delivers to you the solutions, innovations, and a hope for a better tomorrow. Checked It, along with its collaborators, ACM, LNM, IIT Jaipur, Heartfulness Organization, BMSCE, eCell IIT Mandi, IEEE, BMSCE, Code Chef, Microsoft Innovations Club, Music Club, Dance Club, Dramatics Club, VIT Chennai, Skillanta, Ojasvi LPU, and Affinity, branding along with our sponsors, Varivo Motors and EduChecked, brings to you an extraordinary platform where discussions ranging from AI to mythologies will be incorporated among the youth and raise competent minds for the betterment of the future of our nation.
Now, let me introduce our respected speaker for the session, Dr. Vijayalakshmi K. She is an associate professor in the Department of Medical Electronics, BMS College of Engineering in Bangalore. She has a PhD in biomedical signal processing. Dr. Vijayalakshmi has experience in many projects like EEG signal analysis and infrastructure enhancement of biomedical wireless data. She has presented a paper, Quantitative Analysis of EEG Signal before and after Sudarshana Kriya Yoga in the International Conference on Public Mental Health and Neurosciences, and is a recipient of many awards. We are so happy and honored to have you here with us today, ma'am. Now the stage is all yours. Please enlighten us. Ma'am, you're on mute.
Thank you, Shreya and Shuhas, for inviting me and introducing me to the team. Yeah. Can I share my screen? Give a minute. Yeah, I'll share my screen and start presenting. Yeah, hope the screen is visible.
Yes, and
Hello?
the screen is visible.
Okay, okay. Yeah, good evening, everyone. I'm going to just introduce you to the what is a brain signature. As hello, I'm not able to move my screen. Yeah.
Yes, and the screen is changing.
Yeah. It's changing now. Yeah, it's changing. Yeah, just as I've studied and worked in a biomedical area, I would like to share my work experience in EEG domain. As the title says, is a brain signature. We are living beings, human beings. We are going to emit many biomedical signals. Okay, like biomedical signals, as the title says, signal is the one which gives some information. Okay, and it is called as a biomedical because we are taking the signals from the bio living human beings, and as it is used in a medical applications for diagnostic and therapeutic application, it is called as a biomedical signal. Okay, and I would like to, for first few minutes, I would like to talk about what is a signal, how it is acquired. Then I will take few examples of analysis of a brain signature. So when you say signal, in medical field, we have three types of signals usually. Here we have, like, for example, 1D. Okay, that is one dimensional. That is, we have a x-axis and y-axis. X-axis is usually the time parameter and y-axis usually the amplitude. Okay, and here for examples of biomedical signals for 1D are like ECG, EEG, EOG, and EMG. I'm going to discuss what are these signals. And we say we have a 2D signals. Okay, in the 2D signals, examples are like in the form of images. Images are represented in a Cartesian coordinates. Okay, we have a x and y axis, and each dot, or what we call it as a pixel, which gives some information on the value of the information of the signal. Okay. Okay, and we have a 3D images. 3D images, for example, 3D images, again, we have MRI images. Okay, MRI images, when we say 3D, the depth information can be obtained. Okay. And this is about the signals. Okay, then we come to the medical devices. When we go to a hospital, we can see a simple devices to a very complicated device. And all these medical devices are classified based on the risk associated with it. Okay, we have, for example, class 1 equipments, medical equipment. For example, this is a very low risk equipment. And for example, for this is a manual wheelchair. Okay, then corrective glasses, frames, all those which are without any medical assistant, the individual person can use all these equipment. These are low risk and it is classified under class 1. And we have class low risk, medium risk, and low and medium risk. Examples is a personal protection kits and stethoscopes comes under this category. And we have again class 2 medium risk equipments. Example for is orthodontic wise, surgical gloves. Okay, all these examples are the medium risk category. Then we have class 2, medium and high risk, orthopedic nails and plates. These are the examples comes under class 2B. And we have class 3, which comes under high risk. Without any medical assistant, we cannot use this. Example, the pacemakers, okay, prosthetic heart valves, cardiovascular sutures, okay, brain spatulas, okay, all these comes under this class 3. See, all these equipments, we need to take an approval from a FDA, okay, and these we have like 2 FDAs. One is a European and one is US, okay, which gives an approval to use this equipment. Okay, that just I discussed that to complete how the medical devices in which category comes. Okay, now let us go to the signal acquisition system. Okay, what are the system? Like, for example, you might have seen, or we might have seen when we go to a hospital, first thing is they say for any of the diagnostic purpose, if we go to the doctor, first they say go to ECG. Okay, get done ECG. Let us say a layman, we goes to a hospital and sit or sleep for the data acquisition. Okay, we see a big machines. Okay, what is inside that big machine? That is what I'm going to discussing here. The system used to acquire the signal is called as a signal acquisition system. Okay, here the patient. Then we have the front end of a machine, which we have a transducers. You might have seen so many wires they connect. Like, for example, ECG, they connect few leads to the hand and few leads to the chest. Okay, from the wires. Okay, from the wires where the signal goes is the transducers. Okay, here transducers are the one which converts these biosignal or an ionic current, whatever we are measuring from the human beings, to electrical signals. Okay, the transducers which converts from one form of an energy to the other form. Next comes via isolation amplifier, that is isolation circuit. Isolation circuit in the sense, all this machine is plugged to a 230 volt supply. Here we have acquiring a signal from the patient. So in order to prevent any shock hazards from a system to the patient, these isolation circuits have a very high input impedance, and it does not allow current flowing from a system to the patient, so that there is no risk of or scary about a current backflow or a shock. Okay, this is an isolation circuit. Okay, it doesn't allow a current back to the patient. It allows to the ground point. Then we have amplifiers and filters. See, whatever the signal we are measuring from the human beings, they are all of very low amplitude. For example, when we say amplitude, amplitude is measured in terms of voltage. Very low amplitude in the sense it will be having in the order of microvolts, millivolts, and volts. But biosignals will be mainly in the order of microvolts and millivolts. Okay, in order to drive any higher end system, at least we require 5 volts. So from millivolts and microvolts, we need to hike it to a voltage level so that it can be used to driven from the further circuit. So this is a function wherein amplifiers and filters which amplifies the signal. When I say filters, for example, each of the signals, ECG, EMG, they all have a different frequency range. Based on our application, we need to filter out the required signals. These filters are the circuits which allows only a particular bandwidth of the frequencies. That is a function for filters. Then it is given to an analog to digital conversion, wherein the whatever the signal we acquire, it will be in the form of an analog. When we say signals, these can be an analog type or a digital type. Analog signal in the sense it will have a continuous value over the time, whereas digital signal only at a particular instant of time we have a signal, so that we are storing the signal at particular instant of time, so that saving the memory. Okay, and also to process the signal, if it is in a digital form, it is easier. Okay, and also the complexity of processing will be much lower in if the signal is processed in a digital form. So it is converted into, all signals are converted into analog to digital. Then comes filtering to remove the artifacts or a noise. Okay, artifacts, filtering to remove artifacts. Artifacts I'm going to discuss in the next slide. Artifacts are nothing but a noise. Okay, as these signals are of very low amplitude in nature, the external noise are going to embed with the signal. Okay, so we need to remove the artifacts before processing. Then comes detection of event and component. For example, in an ECG signal, what we are interested in only for example, in an ECG signal, we have P wave, QRS complex, and a T wave for a functioning of the atria and ventricles. Okay, in that, if we are looking for only the ventricles function, then we are looking into only the QRS complex. In that case, we need to detect from the overall signal, we are acquiring or filtering only QRS complex to know the functionality of the ventricles. That is nothing but detection of events and components. Next comes analysis of events, waves, and feature extraction. Once we extract the intended signal, we are looking into the wave shaping of the signal as well as the time and voltage parameters. Okay, like for example, each signal has a definite the amplitude and a time signal. Time will be there for a normal signal. If it is going to vary with the normal values, then based on how much variation, the doctors can decide or properly take the decision for diagnosis purpose. Okay, then comes pattern recognition, classification, and diagnosis decision based on whatever the technicians or biomedical engineers design. Here, analysis and feature extraction. Okay, the doctors see the pattern recognition. As I told you, the waveform shape, sometimes they look, and based on that, whether it is a normal and abnormal, they classify and they take a diagnosis decision for a treatment. Okay, this is the full entire system wherein any biomedical equipment comes. Okay, these are the few examples of a biomedical signal. Okay, that is electroneurogram we have from the nerve conduction velocity. It is used to measure nerve conduction velocity. Then we have electromyogram. These are the signals which occur from the muscles. Then we have electrocardiogram. then electroencephalogram, electrogastrogram, okay, phonocardiogram, carotid pulse, vibromyogram, vibroorthogram. All these signals are the different signals obtained by acquiring and placing the electrodes at different place on the body. Okay, but most of the cases, these are the important signals. Even though we have many signals, these are the list wherein the doctors look into. ECG is a signal which are obtained from the heart, and EEG is from the brain, EMG is from the muscle, then EOG is a eyeball movement.
A square minus 2 within. So A square by actually B square.
Hello? Yeah. And we have a GSR, galvanic skin resistance. And apart from the images, if we come, the doctors are looking into X-ray, CT, MRI, PET, and NMR. Okay, these are the main images. And as I told you, this is a signal processing I need to discuss. The first thing is, how do we get the signal from the human body? The thing what we are measuring is an action potential. Okay, this is a cell. Cell has a intracellular fluid, extracellular fluid. This is a cell structure. Whereas extracellular fluid contains abundance of sodium ions, and the intracellular fluid contains abundance of potassium. And this is called as a well. Okay, the sodium potassium well. This is called as a well. And each cell, that is a neuron consisting of a cell body. Then these are the dendrites, which act like an antenna, and these are a axon, and this is a myelin sheath, which is converted like for a, how we have for a wires, insulators are there for surrounding for the wires to avoid a signal leaking. Like that, in a human beings, the signal is transferred through this axon. Okay, and this is in order to prevent a leakage, we have a myelin sheath. Next, each cell, we call it as a repolarization and depolarization. Each cell, for example, whenever a sodium potassium well is get disturbed, okay, then action potential will be generated. Okay, this I am not explaining. I'll just go through directly. This is what the action potential we are measuring. Okay, whenever that cell get disturbed, the potassium ions moves from inside to outside. Sodium ions moves from outside to inside, so that the cell, when it is resting potential, we say it is resting potential. When it gets disturbed, we call it as it is polarized. And again, when it is polarized, again it has to come back to the original state. It is called as a repolarized. Okay, so resting potential, polarized, and repolarized. Okay, so that this is how the signal generated in our cells every time, at every minute and a seconds. Like this, the potential keeps on generating. This is what we are going to measure from placing the electrodes on the body. This is called action potential, which is the ionic current. Okay, and we have electroneurogram. This is from the nerve conduction velocity, as I told you. It is in the order of that is 100 to 300 microseconds rate. It travels. Okay, this is a potential acquired from the nerves. Then we have like the wrist and below elbow and above elbow. This is how if we place an electrodes and try to measure, the signal looks like this. Okay. Then we have electroneurogram. The typical values like 40 to 70 meters per second, where the signal travels in nerve fibers, and it 0.2 to 0.4 millivolts per second in a heart muscle, and 0.03 to 0.05 meters per second, okay, in the fibers, how the signal transmits. Okay, then we have electromyogram. This is a muscle movement. Okay, the motor units, when we contract and relax the muscle, we can recording of this. It looks like this. Okay, then we have this is how it looks. Okay, from different channels we can measure the signal. Then we have electrocardiography, is nothing but an ECG. Okay, this is ECG is acquired from placing an electrode at the right arm, left arm, and right leg, and a left leg. Okay, and this is how the ECG signal looks into. Okay, we have a P wave, QRS complex, T wave, and U wave. Just for a completion, I am going to discuss here. Okay. And this is a normal sinus rhythm of a ECG signal, how it looks. Okay. Okay, this is how. And the ventricular fibrillation is a severe condition where atrium and ventricles beat together rather than flowing in a sequence. This is how it looks. Okay, this is very dangerous condition. If in ECG, this should not come. Okay, yeah. And now next comes to the electroencephalogram. This is what we call it as a 1020 system of electrode placement. This is on the scalp, how the electrodes are placed. We have a frontal lobe, we have a temporal lobe, we have a central lobe and a parietal lobe. Okay. Next comes, we have in an EEG signal, we have like all the signal, like EEG is nothing but, as I told you, it is obtained from the brain. This is what I'm interested, the title is given, the brain signature. Why it is called as a signature? As all of you know, the signature is very unique from person to person, right? So the signatures cannot be same at any time. Like that, EEG signals are also not same for the persons, as it is unique. That's why it is also called, the brain signals are also called as signature, brain signature. Okay. And this has got 4 types of signals embedded in it. Okay, like as I told you, each signal has a voltage and frequency. In frequency category, EEG signals comprises of delta wave, theta wave, alpha wave, and beta wave. I'm going to discuss again later. Okay, electroencephalogram, as this is a signal, this is a alpha, delta, alpha, theta, beta. This is what it looks. Okay, it has got a different frequencies. Okay. Then we have electrogastrogram. Okay. Then we have a carotid pulse, then vibromyogram, vibroortho. Okay. Those are the different kinds of signals wherein we can acquire. As I told you, as a biomedical signals, when we talked about, there are different artifacts or a noise is going to embedded in it. Which are the different types of a noise embedded in it? Because whenever we want to process the biomedical signal, unless we don't know the type of a noise embedded in it, we cannot process it. We have to appropriately clean the signal. Okay, before cleaning the signal, we should know or an idea of what kind of a noises are going to embedded in it. So there are 2 types of noises embedded in it. One is patient related. Okay, that is whenever we are doctors or a physicist are acquiring a signal, if a patient moves, okay, then this movement also causes some kind of a noise on a signal. That's why they say, please don't move for a while. Okay, well, when they connect an electrodes, an instruction given by the attender not to move. Okay, why? Because it's going to embed or introduce some noise in the signal. Then we have a EMG signal, that is muscle electromyogram. Okay, electromyogram. See, whenever they are taking an ECG signal, if we move our hand or a leg, then this causes a noise in the signal. Then we have ECG. Like for example, if we are measuring a respiratory rate, okay, then whenever we breathe in, breathe out, our ECG will also be embedded in it. Okay. Then whenever we are during an acquisition, if we blink our eyes, okay, eye movement also cause some noise in the signal. Then come sweating also, because sweating also introduce some noise, because when we sweat, the impedance of a skin is going to vary. Okay, one example, when we are measuring a galvanic skin resistance, if the person sweat more, okay, then because of the variation in an impedance, definitely it's going to give a wrong value. Okay, these are some examples which the human or a patient itself will add some noise to the signal. Okay, then apart from the patient related signal, we have technically that is technical related noise also going to introduce into the signal. For example, 50 or 60 hertz noise. Okay, like every machine is connected to the power supply. Then power supply will have a constant frequency. If it is in India, it is 50, and if it is in abroad, it is 60 hertz. Okay, So that constant power supply noise is going to be introduced in the biomedical signal. So one of the challenge is to remove any biomedical signal. First thing is we should remove the artifacts of 50 hertz noise. Okay. Then we have an impedance fluctuations. Okay. Like whenever there is a variation in a voltage, that will also cause a all the system or a mini subsystem functions will get affected and it's going to change. So how are we avoiding this? By using a regulator. Okay, the voltage regulators, this fluctuation noise can be reduced. Then cable movements. We should not have a very too long cable also. Usually in a biomedical signal, up to 1 meter is acceptable, not more than that. Okay, because it will have some impedance mismatching and it does not give a proper value. Okay, so cable movements and long cables also introduce some noise. Then broken wire contacts, the leakage, because of the broken wire contacts, so leakage, the signal leakage will happen and it does not give a proper value. And too much electrode, that is jelly, also we should not put, and also low impedance. Next, okay, that is what the two types of artifacts we have learned. Next comes to what are the difficulties of biomedical signal processing, okay, and as well as acquisition. Like any other physical parameters, for example, if we say temperature, the pH value, humidity, all those things can be measured from the outside thing. But biomedical signal acquisition, we cannot take the signals in a like a full noisy place. Okay, so one thing is for many biomedical acquisition system, we have a closed room or a silent zone is created while acquiring a signal. That is one thing. And next, accessibility of the variables to measurement is very, very difficult. Okay, for example, if we want to measure some intestinal signal from the intestine or a heart, it is directly, it cannot be measured. Okay, that's what the accessibility is very difficult. That's why we go for two methods. One is invasive methods and the non-invasive methods of signal acquisition. Usually, in most of the cases, the non-invasive methods are used. That is, from outside the body, from the skin surface, the signals are going to measure. Whenever we want to have a very accurate measurement, then only it's going for a invasive methods. For example, the invasive methods in the sense angiogram, endoscopy, all those like, okay. And variability of the signal source. Okay, variability of the signal source in the sense, okay, for example, if we take the signal acquisition in the morning and evening, then there will be a slight, definitely have a difference in the signals. Then we have an interrelationship and interaction among the physiological system. As I told you, if we want to measure a respiratory signal, definitely ECG is going to embed. And even in the brain signal acquisition, respiratory signal is going to embed it. And also the eye movement is going to be embedded in it. That is because all the systems, sensory systems are interrelated. All some sensory signals from different parts of the body is going to embedded in the whatever the signal we are intended. Okay, then effect of instrumentation or procedure on the system. Okay, there are lot many procedures are there. Okay, even the output varies from one procedure to one procedure. We need to stick on which procedure of processing gives an exact result. That's why in a medical field, still we have known only 10% of the part of the signals. Okay, 90% still it is not explored. Okay, that's why a lot of things or money is putting on to the research. Still we have there is so much to understand. Okay, then we have a physiological artifacts and interference are there. Again, this is a big challenge to get the very clean signal. Okay? And also the thing is patient safety. Okay, we need to give more importance to the patient safety, like all of the physical signals like temperature, humidity. It's not so much safety is concerned, but when we are acquiring a biomedical signal, definitely more amount has to be spent on a patient safety in the equipments. That's why the biomedical equipments cost more, okay, compared to the other system. Next, come to the signal processing. When we say signal processing, we have the first thing comes is signal conditioning. Okay, the signal conditioning consisting of artifacts removing and amplification. As I told you, what is artifacts removing? As I told you, the patient related as well as the technical things which comes into the picture, into the biomedical signal. First, these noises has to be removed to clean the signal. Then amplification and filtering comes. Then comes, we have, whenever we say analysis, there are two types of analysis. One is time domain analysis and the frequency domain analysis. In the time domain analysis, we are going to use either the statistical parameters. I think all of you or many of you know what are the statistical parameters. Like, for example, for the given signal, we can measure like a statistical parameters in the sense we can measure mean, variance, standard deviation, kurtosis. Okay, all those things comes under statistical parameters because those signals give some information. Okay. Next, we have a higher order statistical parameters. Okay, variance, all those things. Okay, still we can measure it, and we have a correlation coefficients. Okay, for example, correlation coefficient in the sense, like for example, we measure a signal from a left side of the brain and right side of the brain. We can measure how similar these signals. Okay, these correlation coefficients measure the how similarity in both the signals. That's what it says. Okay. So in the frequency domain analysis, mainly we have discrete Fourier transform. In short, we call it as a DFT, and spectral estimation and power spectral density and short time discrete Fourier transform. Okay, SDFT and wavelet transform. Like we have so many methods. Okay, based on our application, we need to choose a proper processing steps. Okay, which gives an appropriate or a proper result. Okay, that is again a challenge. Okay, which wherein we can get a signal of intended, and it has to be cater an application for the doctors to diagnosis. Okay, that's where the challenge and most of the research going on. And like for example, even though nowadays we are using a deep learning techniques, there are many methods are there. Okay, and each one gives a different efficiency, and all those things comes in a challenging and the research topic for the students. Okay, now comes now hereafter I am going to discuss mainly on EEG signal processing. EEG is the one which are used to analyze the brain signal. Okay, and when we say brain signal, from the brain, whatever the signal we acquire, what information we are getting, either we can get a structure information, okay, or a function information or a behavior information. That is from the brain signal, either we can go for a structure analysis or a function analysis or a behavior analysis. Again, this is based on for what condition we are looking into the signal. For example, if we want to know the structure analysis of a brain, we have to go for a CT, we have to go for an MRI or diffused attention imaging. Okay, that is DTI. Okay, from doing this, it's not possible to mainly know the function. These methods are mainly dealing with the structure. Okay, structure. Next, if we want to know the function, we need to go for an EEG signal. Okay, electroencephalogram and electrocorticogram, ECOG. Okay, and MEG, magnetoencephalogram, and fMRI, functional magnetic resonance imaging, and PET and SPECT. Okay, functions can be known by these methods. Then if we want to know the behavior of a brain, we need to go for some analysis on cognition, assessment, and retraining. That means by these methods, we can know the behavior of the brain. There are certain tests are there to perform the signal. Okay, that is from the brain signal. There are some certain tests. It is possible to know the behavior of the brain. For one of the example is, for example, ADHD student, okay, attention deficit syndrome student, there are certain tests will be given to just follow up how their after treatment, how their attention things are getting improved. To do that, these behavioral tests are there. Okay? Next, each methods have their own advantages and disadvantages. As I told you, based on what we are looking into, okay, we need to properly select. For example, EEG, it is called as it comes under a direct method, and it has got a good temporal resolution, what we say. Temporal resolution in the sense from time to time, it's from second to second, it's possible to analyze the signal, okay? But it has got a poor spatial resolution. That means as from small space to space, the signal varies, it cannot give exactly the spatial information properly, okay? Because it picks up from the surrounding space also, okay? If we want to from a particular one spot, it is not possible to get a signal. It is nothing but a combination of some 10 mm distance space signal, okay? So it is not a good spatial resolution, but it has got a good time resolution signal, but it is time consuming. Either the doctors go for EEG or MRI. When do they go for or recommend to MRI? Whenever we want to require a high spatial resolution, then the doctors recommend to get it MRI to be done. Then we have should be predictable and zero temporal resolution, okay? As it is, that's why functionality cannot be obtained here. Only the structure information can be got. Like that, we have the comparison between any the other types also. Okay, and when we say EEG signal acquisition, the international standard, what we call it as 1020 electrode placement system. Okay, this is a scan of a person from the top side. Okay, this is a nasion, the nose side, and this is enion from the back side. Okay, head. Okay, from the top, if we look, this is what we get. Okay, and from the nasion, 10% of the distance, that is from the full nasion to anion, they measure it from the they measure it in centimeters, and from this 10% of the total length they take, and this is called as a front portion. Okay, that is prefrontal area. Prefrontal area, that is all the left side is denoted as a odd numbers, okay, suffix, and this is the right side is with the even number. FP1 is odd the left and FP2 is right, okay, prefrontal. Then 20% of the total distance, that is frontal area, F3, F7, F4, F2, like that. And 10, 20, again from this to 20%, this is a central portion, okay, that is CZ, and this is a signal where it doesn't have much of the information, okay, where is the scalp is divided into right and left half, okay, there we have like a mark, okay, in this mark, not much signal information cannot be possible to get. Okay, then we have a temporal portion T3 and T4, T5 and T6, and we have a parietal zone. This is a parietal zone, and this is an occipital zone. Okay, this is how the brain is. In order to study, we have 4 regions: frontal region, central region, parietal region, and occipital region. And this is from the side view how it looks, and this is from the top view. And based on how many electrodes are we are using to place on the scalp, we have different kinds of an EEG machines are there. For example, we have a 2-channel EEG machine. That means only 2 channels at a time only. From these places, any 2 signals can be acquired. Then we have 8-channel machine. Then we have 16-channel machine, 24-channel machine. Then we have 68 channel, 128 channel. Now we have the maximum 256 channel machines are available, and based on the channels, how many channels we are using it in a machine, likewise the cost goes high. And just for your kind information, EEG machines are now available with 2 lakhs to 5 lakhs, up to 10 lakhs also. Okay, like if we go for a higher end, definitely the price of the machine goes high. Okay? And what are we looking from the brain signals? Okay, our brain signal, as I told you, first of all, it is divided into left half and right half. Okay, and again, based on the 4 regions, lobes are there. Okay, left brain. If we are looking for, okay, for logic thinking of a person, we need to go for left channels. Okay, analysis need to be taken from the left side of the brain. Then a logic, some mathematical analysis is given, then sequencing, linear, or then math doing, then language, then facts, thinking words of song, okay, comprehension, all these things, most of the left brain function. Okay, then in the right brain, for example, creativity. Many of the artists, if we look into the drawing, writing, okay, creativity, most of for them, the right activity will be more for them. Then imagination, then holistic thinking, then intuition, arts, okay, then rhythm, non-verbal, feelings, visualization, all these, if we want to analyze, we have to go for right channels. Okay. Then, as I told you, each of the lobes or each of the place will have some definite functions. For example, F7, some rational activities, and F8, okay, then emotional impulse. Okay, then T3 and T4 emotional processes are located. For example, nowadays most of the emotional analysis is being done. For that, instead of analyzing from the signal from the many places, just T3, T4 analysis we can look into. Then T5 and T6 certain memory functions stand. Okay, for example, memory functions in the sense some mathematical thing is given, or some external audio stimulus is given, or video stimulus given, just to check how much memory he is having. Like, for example, repeatedly they show a few images. Okay, they repeat the same thing. Then they will ask whether this image is first time shown or the second or third time shown. Like that, just to check the memory thing. For example, like Alzheimer patients, okay, they have a very less the memory thing. For Alzheimer patients, we can look into T5, T6 instead of looking into all the other places signal. Okay, then primary visual areas can be found below the points O1 and O2. Okay, if we have a visual impairment, then we can go for O1, O2, say O2 channel analysis. Okay. And like next I will take you through EEG waves. Okay, just when I say EEG, it is not possible to get all the information. Again, the whole entire EEG has a bandwidth of 0.5 to 40 hertz signals. Okay, and in that, again, it is divided into 5 main types. When we say alpha wave, see, alpha wave has a frequency range of 8 to 13 hertz, and the amplitude is 20 to 60 microvolts. What is alpha wave depicts? Okay, it is easily produced when quietly sitting in relaxed position with eyes closed. That is, the best example is when the person is very much relaxed, his alpha wave energy will be more, or alpha wave power will be more in the person. Then alpha blockades occurs with mental activity. Okay, so this is an alpha wave. Then we have a beta waves. So beta waves have a different frequency range, which in 14 to 30 hertz. Again, amplitude 2 to 20 microvolts. When does beta waves occurs? In the most common form of brain waves, okay, these are the one, and are present during mental activity. For example, a whole day, if a normal person, for example, if he is more active, then definitely beta waves will be more. Okay, if they are like not active or sleepy, then definitely beta waves will subside, and the other waves will be dominating. So next comes to the theta waves. The theta waves has a frequency range of 4 to 7 hertz, then amplitude of 20 to 100 microvolts. Then it is believed to be more common in children. Okay, children than adults. Then okay, these are the theta waves. Then delta waves, it is a very low frequency range. You can see that low frequency, and it is from 0.5 to 3.5 hertz. Okay, frequency. Then amplitude is 20 to 200 micro. Then when does these more wave pattern is found during periods of deep sleep in most people. Okay, and if we look into the children, the very small, the newborn baby, the delta waves will be more for them. Then And even for the adults, if they are as I told you, the mental blocks are there, then if very low active persons, and almost all the time the delta waves will be dominating for such persons. Okay, then any mental illness are there for such persons also, the delta waves will be very less. Also useful in detecting tumors and abnormal brain behaviors. Okay, so delta waves will be studied. And these gamma waves are characterized with a very high frequency, 36 to 44 hertz, okay, occur with sudden sensory stimuli. For example, if we suddenly see a snake coming on the road, definitely our frequency range goes very high to alert this one, okay. We need to keep alert ourselves. In that time, definitely gamma wave shoots up, okay. And this is, okay, just I will show you, take you next few slides, how these artifacts or EEG looks like, okay, like EEG artifacts, okay, like see here, this is a continuous wave, this is like a artifacts, okay. Then see this at the left hand side, we have a different FP1, FP2, F3 frontal central region. If you see no signal here, then okay, then P3 parietal, T7 temporal, T8. So if we see blink our eyes, as we blink our eyes, since the prefrontal electrodes which are placed on this very near to the eye, we can see that eye blink will be dominating in the prefrontal areas. It is not going to reach the F3, F4, C2. So these are the eye blink which are, if purposely done or not done, okay, anyhow, these placements of electrodes are near to this, to the eye. These are going to be depicted in the prefrontal area. Okay, then eye movement. If we move it very fast, okay, just eye blink is a slow movement. Eye movement is nothing but a left, right, up, down, like that. If we move, definitely the signal reaches to F3 and F4 levels also. Okay. Then muscle artifacts. See, if we move our muscles, okay, contract and relax, definitely it is going to affect the entire region of the brain. Okay. Then recording. Okay, these are a few of the examples how the artifacts will be included in the signal. Next, we'll see how do we acquire the signal from the scan. We have what is called as a disposable gel-less and pre-gel types electrodes are there. Okay, and there are disc type electrodes. And again, the material used for the electrode is gold, silver, stainless steel, or tin. So we cannot in the hospitals, few very high priced equipments. Definitely they use a tin or a gold. Okay, very accurate signals can be got by this. Otherwise, in the laboratory and all, what we use machine, we have silver chloride electrodes. Okay. Then nowadays the head bands are available and head caps are available, which are very easy to put in and acquire the signals in an easy manner and a very quick. And we have a saline based electrodes and needle electrodes. Okay. See this, when I say disc type of electrodes, these are the one which they put some paste or a jelly and these fixed onto the scan. Okay. Tin plated, tin, silver, gold plated. Gold plated are very expensive. Each one electrode costs 2,000 rupees, whereas silver chloride cost 25 rupees. Okay. And once we have from these electrodes, if we acquire the signal, next for processing, we need to store these signals. As I told you, when the signal which are acquired will be in the form of an analog signal. Okay, in order to digitize, these has to be transferred to the system. Okay, there are different machines are available which can store the signal in these formats. Like for example, we have a .dat format from a biologic brain atlas, and we have a .raw format, the Compute Medical Limited machine if we take, and we have an EDF, that is European data format. Okay, this from the track kit if we acquire the signal, and we have a neuroscan .cnt, .eeg. Like each machine has its own way of or data formatting and storage of a signal. So whatever the platform we are working, first we need to check whether my platform supports these signal types. If it is not, okay, then we need to have convert from these form to the supportable format in the platform wherever we are working. For example, Python, MATLAB, okay, Colab. There's so many Google Lab. There's so many platforms are there. Okay, we need to first convert if it is not supporting one kind of data format to the other. Okay. So next, after knowing this, what are the applications of EEG? Either these EEG signals can be used in research or health or medical and human-computer interaction. Okay, now the human-computer interaction, the BCI application. Okay, when we say research, again, schizophrenia, Alzheimer's, to find the tumors in the brain, okay, all those comes under a research area. Then health and medical, again, the doctors are using the acquired signal for the diagnosis, and human-computer interaction, wherein for paraplegic patient, we can generate a control signal from these brain signal just to have a movement or to control some, for example, to switch off the fan, to move from the wheels from one position to one position. Just with the brain signal, it's possible to get this brain-computer applications. Okay. Next, just in a few slides, I am going to explain what work I have done with. Okay. The one work which I have done is a quantitative analysis of brain electrical activity on meditation. This is done as a technical support to the art of living. You know, for art of living, they are the one which are most effective in teaching the Sudarshana Kriya Yoga. They wanted these signals to be analyzed, EEG signals to be analyzed when the person is performing Sudarshana Kriya Yoga. Okay, so that's what the meditation analysis, what we did. There are different types of a meditation. Okay, and yeah, this is how we used a 8-channel AD instruments to acquire the signal. Okay, we see the acquired signal. This is how it looks. We cannot understand anything. This has to be digitized and processed in order to understand the signal content. Okay, and what did we do? Okay, as the meditation is nothing but it is a relaxed state. Okay, again, it based on the subject. If we do seriously, the person does the meditation seriously, then definitely they are relaxed. Okay, and the beginners, definitely they need some time to get deep into the meditation. They'll take some time. Okay, so what kind of EEG signals are analyzed for the meditation thing is alpha wave and the beta wave. Okay, because alpha waves are nothing but the signals which depicts or which will have a more signal strength when the person is relaxed. We analyzed alpha power of a signals. Okay, first we did for pranayama, like for example, we measured a alpha wave before a pranayama and we measure a alpha wave after a pranayama. This is a signal strength what we observed. Okay, before it was lower and after the pranayama, definitely, or it is not like hypothesis. We expect alpha wave to be increased if they are relaxed. That's what we found that. Okay, before pranayama and after pranayama, how much there is a increase in a signal strength. That is what we measured. Okay, pranayama. Okay, and also we measured beta power before and beta after. As beta is a power or a wave when the person is very active. If they're relaxed, definitely beta power has to be reduced. That's what before the beta power were very high and after the pranayama, the beta power was low. That's what we observed. Okay, and this is what is called as a topo plot. There are different open source softwares are there wherein we can, if we give the signal, these kind of a topo plots, the colorful plots can be seen, and this shows the strength of a signal in the front region or a temporal region or an occipital region. A red indicates a high strength, blue indicates a lower strength. We can see the energy distribution of a signal on a scale. Okay, and this is 9.4 hertz, 14 hertz, and 21 hertz. Okay, and if you see the alpha wave is 8 to 9 hertz. Okay, we see that alpha wave for this kind of a signal, the frontal portion is very high. Okay, and in this the frequency here 21 hertz comes the gamma wave. We can see that when the person is active, usually the temporal and the central region makes a very high strength. Okay, this is how with the topo plot we can see the energy distribution over the entire skull. And again, this is a topo plot at different instance of time. We can see, okay, after a meditation, we could see that after some time there is an energy hike in the frontal region. Okay, this is what, and even the right side, we can see that the right side, as we say, when the person is relaxed, we expect the right side signal has a more strength. Okay, this is what in a few of the channels, definitely the strength indicates the right side. Okay, and we did again for the long-term practitioners and the short-term practitioners, what is the difference between, or how does the difference between the central region or a frontal lobe or a right frontal, occipital lobe and occipital right, just to know the distribution of before and after the meditation. We could also perform this, and from this we saw that for a long-term practitioners, all the brain regions are more active. Okay, or else it shows more power than the short-term practitioners. Okay, but in a short-term practitioners, in the sense those who are practicing for less than 1 year, we took, and for practicing more than 8 years, we took as a long-term practitioners. Okay, again they showed overall in a almost all the regions their energy levels were high compared to the short-term practitioners. Okay, this is what we could do, and this is a trend plot wherein the entire Sudarshana Kriya, we have a different stages. Okay, like for example, Pranayama 3 stage, and Brahmari, Om, Hara, and this is again the breath cycles, fast and slow breath cycles we have, Soham, and again we have a post Kriya and Yoga Nidra. Okay, during all the time, we can see that the green one, alpha wave, is dominating. If we see that the red is theta and the delta is the blue one and the alpha is the green one, during the entire region, we can see in almost all the time the alpha wave is dominating. That's what. And Bastrika, as it is some kind of a hand movement is there, we can see the beta power, that is beta power, because the hand movement is there. We could see the hike in the signal strength. Okay? And this shows if the person is definitely relaxed, the alpha wave shows a domination in the amplitude. And this is done, this kind of a plot is done for 43 subjects. We did an analysis which part of the brain is more active during the that is after Sudarshana Kriya. Okay, here we took the signals from all the 4 regions of the brain. Okay, and if we see that the right frontal area, which is orange portion, okay, for almost all the 43%, we see that the energy level hike is there in the right frontal area. Okay, this is the hypothesis made in one of the paper. We also just did the analysis, and we also got the same thing, whatever the hypothesis is made. When the person is more relaxed, definitely his right brain activity is more. Okay, this is also for a comparison between a short-term and long-term practitioners also we could do this. Okay, and this shows the scientific evidence of convincing that yes, definitely meditation has some effect on the person, and it is scientifically how our brain signals will alter itself to manifest the effect of meditation. Okay, this is what we want to show that. Okay, and again the frontal left and frontal right, we measured this. Okay, and again this is this is one kind of a plot. Okay, and this is again EEG signals are done for a sleep analysis. Okay, during the sleep analysis means if the persons are not getting a sleep properly the whole night, nowadays we have a sleep labs are there, wherein along with an EEG signal, we have other signals are also measured, respiratory signal, pulse rate, all the signals are measured on a single plot, and it will give one ratio. Okay, so that based on that ratio, whether he is how much sleep pattern, that is sleep pattern analysis can be done for the entire 8 hours analysis done. Okay, in that also the EEG signals are used. Okay, and again there are other applications where BCI applications, and we have a neurofeedback applications. Okay, for all gaming and all, they use a neurofeedback application. Okay, and overall the big picture is we have a database seed, and the first thing from the database or acquired signal, we remove the artifacts, and after removing we process whether it is a time domain or a frequency domain. Then we have a feature extraction, again that goes to the database if it is a very good process, and that is what hemisphere and lobe analysis what we are doing from the feature extraction. This is a big picture. We have the entire from acquisition to analysis. And here are some of the textbooks. Just I'm going to share the slides. If any of you are interested, to begin with, definitely these books are going to help you. Biosignal and Biomedical Image Processing by John Semlo. There are many MATLAB exercises given there. And we have a biomedical signal analysis by Rangaraj Rangayan, where few data sets are there in the textbook link is given. Just to begin, we can start up doing work. And also biomedical signal processing by DC Reddy is a very good book to know the theory part of it. And we have a biomedical digital signal processing by Tompkins. These 4 books are just to beginners. It's definitely going to. And there are certain data sets are available in a PhysioNet, okay, biomedical data bank, wherein we can download and we can start using those signals to understand the signal. Not only EEG, we have ECG, many types of biomedical signals can be done. Now the CATL is also there, okay, and there are many open source softwares are also there, wherein you can use it for analysis. Okay? And the one thing just want to tell you, if you are interested, definitely I suggest you to visit NIMAS, where they have a brain museum. Okay, many don't know. Just we every year we take our students to show the brain museum. Okay, Neurobiology Research Center is there in the NIMAS, and just we can touch and feel all the parts of the body like medical students. Okay, like how they give, we can just see. Okay, the brain museum is very informative museum they have. Okay, they'll explain very well. Those who are interested, definitely one should visit that. Okay, just to have a look. Thanks.
Ma'am?
Yeah. Thank you. This is end of my slide. Now I'm open for any questions, please. Yeah.
Thank you very much, ma'am.
Hello?
It was definitely an
Your
amazing session. And
voice is
breaking, ma'am?
Saharsh? Yeah.
Any better?
Yeah.
Okay. So, ma'am, that was an amazing session, definitely. And the work you are doing is definitely useful for the mankind. So thank you very much, ma'am, for accepting our invitation. I will invite Anushka to give vote of thanks, ma'am, because of the time crunch, we may not be able to have a Q&A session. However, we will submit all the questions over email to you so that we may hope for an answer. Anushka, can we please have a vote of thanks very quickly?
Yes.
Thank you, Anushka.
So, So firstly, thank you, ma'am, for taking out time from your busy schedule and for this amazing, enriching and intense session. Now I would request the team to please share their screen and provide ma'am with the memento. Nextly, yes, ma'am, this is for you. Please take this as a token of our gratitude.
Thank you. Thank you.
Yes.
Thanks. 80 from your end.
Yeah. Nextly, I would like to thank our mentor, Dr. Rajeshwari Hete and Dr. Susan Elias for guiding us throughout so that our team could execute the dreams. I would extend my thanks and gratitude to our lovely sponsors, Verivo Motors and EduChecked, along with all of our collaborating organizations. Thank you, everybody. Without you all, we could have never achieved this kind of an event. And most importantly, I would like to thank the outstanding audience. Thank you guys for attending the session and stay tuned for what we're bringing to you next.
Hello. Thank you, Vijay Lakshmi ma'am, once again. Acha ma'am has said. Achut, we can end the live and quickly start the next live. I hope everybody would be extremely excited and enthusiastic for our final valedictory ceremony. Guys, I know we have come a long way. Achut, Anushka, am I audible?
Yes, you are.
You are audible.
Okay.
Yeah.
Achut, can we
1 minute.
quickly start